In this video, we're going over implement trie. So a trie or prefix tree is a tree data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications of this data structure, such as autocomplete and spell checker. We'll implement the trie class, we'll initialize the trie object, we'll insert a word, search for a word, and we check if a word starts with a certain prefix. Let's go over the thought process. So a prefix tree is a tree which contains nodes, and we call this trie nodes. Each of the nodes inside the tree represents a character inside a word. Now a path from the root node down to any of the nodes represents the prefix associated with a word. Now for each of the node X, we will need to check if the character C exists. We will need a quick way to check the node associated with character C. Or we can say it's a children node associated with the character C. We can create a hash map inside the node to map C to a children node or a children trie node. This will allow us to quickly search for the next character inside a word. Now, how can we know if we have found a word? Each of the nodes can have a Boolean flag to indicate if the current node is the last character of a word or not. So for example, if we have the word X, Y, and Z, the node associated with Z will have a Boolean flag of true to indicate that this is the last character inside word. And the root node does not have a character. Now let's go over the pseudocode. So we're going to create the following fields. The first one is the root node. We're going to create a custom class. So we're going to create a custom class trie node, which is the nodes inside the prefix tree, and there will be the following fields. We'll need a children, which is a hash map to keep track of character to a children node or a children trie node. And we also need is word is a Boolean flag to indicate if we have found a word. Now we're gonna initialize the root node. We can call this the root trie node. And then we're gonna insert a word. So we're gonna create a variable node to keep track of our current location inside the trie. So it will be initially at the root node. So we're gonna initially start at the top of the tree, and then we're gonna insert this word. So creating a path downward. So we're gonna iterate through the indices of word denoted as I. We're gonna retrieve the current character C. Character C at index I. Then we're gonna put C in a new trie node into node.children if it does not exist. So if the character C does not exist inside node.children, we're going to put a new children node. This will allow us to create a new path downward. Then we're going to set node to node.children.getC. So currently we are moving down the trie. Then after we have performed this operation, we have reached the last node. And when we reach the last node, we want to set the Boolean flag to true, because we just to indicate that the current character is the last character inside the current word. So I'm going to set node.isWord to true. Now our next method is searching for a word. So we're still going to create a variable node to keep track of our current location. And then we're still going to iterate through the indices of word. And then we're going to retrieve the current character C at index I. Now if node.children does not contain C, this means we do not have we have failed to find a path for this word. So we have failed to find a word. So we can return false. Now I want to set node to node.children that gets C. We are moving down the prefix tree. Now, after we have reached the last node, we want to check if we have reached the last character. I mean, we have found the word or not. And we have only found the word if node.isWord is true. So we only return true if node.isWord is true. Else return false. Now we're going to find a prefix. Now we are trying to find a word with this prefix. So we're still going to create a node to keep track of our current location inside the trie. And then we're going to iterate through the indices of prefix in this case. And then we're going to retrieve the current character C at index I inside prefix. Similar, if node.children does not contain C, we have failed to find a path. This means the prefix does not exist. So we're going to return false. Then we're going to set node to node.children that gets C, moving down the trie node. Then we only return true. Now we have reached the last node inside the prefix. So we are just going to return true because we do not need to check if the current node is actually a word or not. We just need to check if the current node is a prefix. So, and since we have found the last character of the prefix, so we have found the prefix. Now let's go over the time and space complexity. For the time complexity, for our trie, we have first have to go to our space complexity. For space complexity, we get O of n, where n is the number of nodes. This is because of our prefix tree. And then when we insert a word, the time complexity we get is O of k, where k is the length of word, because we process each of the characters inside word. And then for searching for a word, the time complexity will be the same, since we process each character inside word when we search for it. And then we'll check if a word starts with a prefix is also O of k, where k is the length of prefix, and then we process each character inside the prefix. Now let's go over the code. So we're first going to create our custom class, trie node, to represent the nodes inside our current trie. And then we're going to following fields. The first one is our children hash map, where we keep track of character and the children trie node. And then we also have a Boolean variable, is word, which will initially be false. And then we can create a constructor where we initialize the children hash map. Now we're going to start creating the field inside our trie, which there's only one field, which is a root node. And then we're going to initialize the root node inside the constructor. Then we're going to insert a word. We're going to create a variable node to keep track of our current location inside our trie, which will initially start at the root node. And then we're going to start finding our path downward down the trie. We can iterate through the indices of the word. We're going to retrieve the current character at index I. Now we'll put C and a new trie node if it's absent, basically creating a path downward if C does not exist at the current path. And then we're going to move downward in the path. After we have reached the last node, we need to set the Boolean flag is word to true, just to indicate that we have found the word, just to indicate that the current last node is a word. Now we want to search for a word, similar case here. We're going to create a node to keep track of our current location. Then we're going to iterate through the indices of word. We're going to retrieve the current character. But now in this case, if node.children does not contain C, this means we have failed to find a path. If we have failed to find a path, we have failed to find a word. So we're going to return false. And then we're going to move downward through the prefix tree. And then we're only going to return true if the current node represents a word. Now we're going to check if there's a word starting with this prefix. So similar case here. We're going to create a node to keep track of our current location starting from the root node because we're moving downward again. And then we're going to iterate through the indices of prefix. And then we're going to retrieve the current character C. If node.children does not contain the current character C, we have failed to find a path, which means we have failed to find the prefix. We're going to return false. And then we're going to move downward to the trie. Then we're just going to return true because we do not care if the current node represents a word or not. We just need to find a prefix of a word. Let me know if any questions in the comment section below. Like and subscribe for more videos that will help you pass the technical interview.